In this video, we are going to talk about residues at infinity. This is the overview slide, which we'll spend about 5 minutes on before we go over each of these topics in more detail and with more examples. Actually, this is a fairly short video, so I can outline what we're going to do with more detail. First, we'll sort of derive this formula. Second, we'll take a closer look at this example. Here in the overview, and on this overview slide, I only did this example using this residue at infinity formula, but later in the details of the video, I also compare the calculation using Cauchy's residue theorem, which we had done in a previous video, but I just bring that up again just for comparison. And then finally, there's one more example. In this video, we talk about residues at infinity, which is designated or denoted with this residue z equals infinity of f of z. We have this theorem: if a function f is analytic everywhere in the finite plane except for a finite number of singular points interior to a positive-oriented simple closed contour C, and this is our picture, this is our contour C, so there's a finite number of singularities here, but otherwise everywhere else f is analytic, then the closed contour integral around C is equal to 2 pi I residue at z equals 0 of the function 1 over z squared f of 1 over z. You can see this formula is very similar to Cauchy's residue theorem, which I've pasted here just for comparison. Again, we have C, a simple closed contour. Function f is analytic inside and on C except for a finite number of singular points inside C. Then we said the closed contour integral f of z dz is equal to 2 pi I, the sum of all the residues of the singular points inside C. So when you have a lot of singular points, you can see how this formula might be easier to use because it involves only one residue. This residue here, the residue at z equals 0 of 1 over z squared f of 1 over z, which I have copied over here, that's equal to the negative residue of z equals infinity f of z. So this is how we define residues at infinity. And again, so we consider a function f of z having a residue at z equals infinity when f of z is analytic everywhere except for a finite number of singular points that are enclosed in some contour. So here we might have a few singular points, a finite number of singular points. It could be a lot, but they're finite. Everywhere else outside the contour up to infinity will be analytic. I have an example to show you how this works. So we're going to evaluate the integral f of z equals 5z minus 2 divided by z times z minus 1 around the contour modulus of z equals 2, described in the counterclockwise direction. Later in this video, in the details, we'll compare this calculation here to the one we had done earlier using Cauchy's residue theorem. Our function f of z has two singular points at z equals 0 and z equals 1, but since we're using the residue at z equals infinity, which is related to residue z equals 0, we're going to center our Laurent series at z equals 0, since this is the only singularity now that we are going to be looking at, z equals 0. And what I need to look at is the function 1 over z squared times f 1 over z. I have my 1 over z squared, and then plugging in 1 over z here for z, I have 5 times 1 over z, which is just 5 over z minus 2, divided by, now I have my 1 over z times 1 over z minus 1. The rest over here is algebra until I get to 5 minus 2z divided by z times z minus 1. Because I want to use this form for my summation, my series form, I'm going to separate out my fraction so that I have 5 minus 2z over z times 1 over 1 minus z. Now here, this perfectly fits my form, Also here I can simplify this to 5 over z minus 2. The 2 is just a scalar multiple, so that's fine. And 5 over z is exactly in the form I want. It's centered at z equals 0. And now I plug in my summation formula, and I get the summation n equals 0 to infinity z to the n. I write out a few terms of my summation, and I look at my 5 over z minus 2 times my 1 plus z squared. And I'm looking for my residue, which is the coefficient of the z to the minus 1 term. So you can see when I multiply 5z times 1, I'm going to get a z to the minus 1 term, and my coefficient will be 5. When I multiply anything else, I'll get either z to the 0 exponent or z to a positive exponent. Similarly, when I multiply negative 2 times anything in my series, I'm going to get positive exponents or z to the 0 exponents. So my only factor that's going to contribute to my residue is this 5 times 1 over z. So the residue is equal to 5, which means the closed curve integral of 5z minus 2 over z times z minus 1 dz is equal to my residue 5, and then over here, times 2 pi I, which is equal to 10 pi I. So this wraps up our overview, so now we can take a closer look at how this form is derived. We are going to start with the function f that is analytic throughout the finite plane, except for finite number of singular points interior to a positively oriented simple closed contour. In our picture here, here's our closed contour C. So inside, there might be some singular points, but there's only a finite number of them. Everywhere else, our function is analytic, everywhere else outside C. Next, we're going to let R1 denote a positive number. It's a radius, which is large enough that C lies inside the circle modulus of Z is equal to R1. So here's our R1. So it's a circle of radius R1, which is big enough to enclose C. Remember, F is analytic everywhere except maybe those singular points contained in C. So the next point is the function is analytic throughout the domain Z, modulus of Z is greater than R1 and is less than infinity. So that's this green area. Everything greater than R1. And actually F is, analytic in even more area than this, but it is certainly analytic in the green area. Now we let C0 denote a circle of radius R0, and that's out here. Oriented in the clockwise direction where R0 is greater than R1, then the residue at infinity is defined by the means of the equation. The integral of C0 f of z dz is equal to 2 pi I residue z equals infinity of f of z. Now, since f is analytic throughout the closed region bound by C and C0, so this C and this C0, so we're looking at this region here, we're analytic here. By our principle of definition of paths, that means the integral of C f of z dz is equal to the negative integral at C0 f of z dz. And this negative C is because C0 is in the opposite orientation as C. And for your reference, I have our principle of definition of paths here. This is from our previous video in chapter 4. So we said let C1, which looks like a tree, and C2 both denote positively oriented simple closed contours where C1 is interior to C2. So if a function is analytic in the closed region consisting of those contours and all the points in between, over here, as well as the contours, then essentially we can deform this path C1 until it becomes C2. So the closed contour integral of C2 of f of z dz is equal to the closed contour of C1 f of z dz. And again, the idea is you're deforming this path, which is called path deformation, of C1, you're stretching and pulling it until it becomes C2. And as long as you're stretching and pulling it into areas where f is analytic, you're good and you can use this path deformation theorem. So this is what this is saying, that this C1 can be stretched until it becomes the C0 circle over here. But since C0 is in the opposite direction, we have this negative. And it is this integral here that we defined as our residue at infinity. And I kind of think of this as our C0 here. We're letting our radius go out to infinity. So here we have then the integral of c f of z dz is equal to minus 2 pi I residue at z equals infinity f of z. To find this series, we need the Laurent series, which in the general form is n equals negative infinity to infinity c sub n z to the n. Before we broke apart our a sub n, our analytic portion, so we would go from n equals 0 to infinity, and then we had our principal part where we went from n equals negative infinity to 0. Here we just combine them all and call them c sub n z to the n, and then we go from n equals negative infinity to infinity. This is our formula then for our c sub n coefficient, 1 over 2 pi I integral negative c naught f of z dz z to the n plus 1 for n equals 0, plus or minus 1, plus or minus 2, etc. And z is between r1 and infinity. So sort of again, the idea is r naught goes out to infinity. And the first thing we're going to do in this formula is replace z by 1 over z, then multiply the entire equation by 1 over z squared. So here's my 1 over z squared, replacing z with 1 over z. So I get 1 over z squared, my summation c to the n, 1 over z now to the n. Combining this 1 over z squared with my 1 over z to the n, I get summation n equals negative infinity to infinity, c sub n 1 over z n plus 2. And because we often want this index to start at n equals, not to have the n plus 2, but z to the n, we're going to walk back our indice. We're going to subtract 2 from here, but it gives us still negative infinity. But here, we subtract 2 from here, c sub n minus 2, and then this becomes 1 over z to the n. So it's just index manipulation of these summations. Because I am interested in the coefficient of the minus 1 term, in other words, when n over here is equal to, n over here is equal to minus 1, I'm interested in c sub minus 1. So here, for c sub minus 1, I have 1 over 2 pi I, integral minus c naught f of z dz. Now when n is equal to minus 1, this becomes z to the 0 power, which is just equal to 1. So then I have my closed curve integral f of z dz, multiplying my 2 pi I over on this side, I get minus 2 pi I, the residue at z equals 0 of my 1 over z squared f of 1 over z. Since this over here is equal to minus 2 pi I residual of z equals infinity f of z, when I compare that to here, that means the residual of z equals infinity f of z is equal to the minus residual of z equals 0, 1 over z squared f of 1 over z. And this is how we derive or come to this formula here. The residual for z equals infinity is equal to the negative residual z equals 0 of 1 over z squared f of 1 over z. I have our theorem here that says our closed curve integral of f of z dz equals 2 pi I residue at z equals 0, 1 over z squared f of 1 over z, and I remind myself that this residue is equal to the negative residue at z equals infinity. Now we can do our example. Evaluate the integral f of z equals 5z minus 2 divided by z times z minus 1 around the circle of radius 2 described in the counterclockwise direction, and we'll compare this calculation to an earlier calculation from a previous video where we used the Cauchy residue theorem. The first thing to note, f of z equals 5z minus 2 over z times z minus 1. The f of z has two singular points at z equals 0 and z equals 1. But since we're using the residue at z equals infinity, which is related to the residue at z equals 0, we are going to center our Laurent series at the singularity z equals 0. The first thing I'm going to do is calculate my 1 over z squared times f of 1 over z. So I have my 1 over z squared, and then I plug in 1 over z into my f of z. So I'm going to have 5 times 1 over z, which is just 5 over z, minus 2. And then I'm going to have 1 over z times 1 over z minus 1, which is here. The next thing I did is I multiplied this 1 over z times 1 over z minus 1. So I have my 1 over z squared minus 1 over z. And then I multiplied my numerator here by my 1 over z squared. So I end up with 5 over z minus 2 times 1 minus z. I multiplied this fraction by z over z to get 5 minus 2z in the denominator. In the numerator, I'm going to get z times 1 minus z. And so that I can get this fraction where I can use this series formula, this 1 minus z is good. It's in the correct form. So I'm going to separate my 5 minus 2z divided by z from that. And then I still have my times 1 minus z. So this is good, ready to go. This here actually is pretty easy to simplify. So this 5 minus 2z over z simplifies to 5z minus 2, and this 1 over 1 minus z becomes our summation then, n equals 0 to infinity of z to the n. I expand this series out to 1 plus z squared, and I still have my 5z minus 2. And remember, to look for the residue, I'm looking for the coefficient of the z to the minus 1 term. So when I multiply 5z times 1, I'm going to get a z to the minus 1 term, so the coefficient is 5. When I multiply this 5z times everything else, I'm either going to get z to the 0 or z to the positive power. So none of this is going to contribute to my residue. Similarly, when I multiply negative 2 by this series, I'm not going to get anything with a z to the minus 1 power. So 5 over z times 1 is the only term that contributes to the residue. And the coefficient of that residue is equal to 5. Now by my residue at infinity theorem here, the closed curve integral of 5z minus 2 over z times z minus 1 is equal to 5 times 2 pi I, which is equal to 10 pi I. I'm going to redo this example now using Cauchy's residue theorem. And the first thing I want to do is identify my singularities at z equals 0 and z equals 1. Both of these singularities are inside our circle with radius 2. I'm going to start with my singularity z equals 0, so I'm going to center my Laurent series around my singularity z equals 0. Because I'm going to be using my 1 over 1 minus z is equal to the summation of z to the n, I'm going to put my function f of z, again, no longer 1 over z squared f of 1 over z, but just the plain function, into this form here. So I first separate out my two fractions, 5z over my denominator minus 2 over my denominator. I factor out my 5, and in this fraction I factor out my 2z. My 2 over z is not a problem since I'm centering at z equals 0, so I want my terms to look like z minus 0, or in other words, look like z. So this is good. My z minus 1, I need to have this in the 1 minus z form, so I'm just going to multiply by a negative 1, which will make this positive, and then I have 1 over z minus 1. Similarly, over here, I multiply my 5 by a negative, so this can become 1 over z minus 1. And now I can use my summation formula. I have negative 5 sum of z to the n plus 2 over z sum of z to the n. I expand out my two summations. I can see this 5 times this summation here. I'm not going to have anything with z to the minus 1 power, so this is not going to contribute to my residue. Over here, my 2 over z times 1, that will contribute to my z to the minus 1 power. Nothing else will. So 2 then is going to be my residue for my z equals 0 singularity. So I've noted that here. My B1, my residue, at z not equals 0 is equal to 2. But I still have this other singularity at z equals 1. So I need to center a Laurent series around z equals 1. Which means over here in my numerator, my 5z minus 2, this z here needs to become a z minus 1, which means I have this extra minus 5 term, so I'm going to need to add a 5 back. So I'm going to combine that with my negative 2. Down here, this z minus 1, that's good, but this z minus 1 also needs to become a z minus 1. But when I do that, and I multiply this, that means I'm going to have this extra minus 1 times z minus 1, which means I need to add another term of 1 here. So this is z minus 1 plus 1. This came from this z, but I wanted the z to have the z minus 1 form. Then next I have some algebra, and I separated this out again, aware that I want to use the summation formula. And I've grouped this way because my 5 is just a multiplier to my summation, so that's fine. I also have this in the form that I want, which is just a constant over z minus 1. That's fine. So what I need to do is put this 1 over 1 minus z into the form of 1 over 1 minus some simple function of z. And actually that's exactly what this is. This is 1 minus, and now we're going to replace this z with 1 minus z. But there is something I need to be aware of. I'm centering my function at z minus 1. So this is what I need my powers of z to be equal to. I don't want 1 minus z, so I need to throw in another negative sign. So this can become z minus 1, which again is what a series centered at z equals 1 looks like. So to choose, I throw in a negative to convert this to z minus 1, but that means I have to have another negative 1 in front. So this is algebraically equivalent. And now I can substitute my minus 1, z minus 1 for z in my summation formula. And what I get then is my 5 plus 3 over z minus 1 summation negative 1 to the n, and then my z minus 1 to the n, which is 5 plus 3 over z minus 1. My negative 1, or when n is equal to 0, I have 1 times 1, which is 1. When n is equal to 1, I'm going to get a negative z minus 1. When n is equal to 2, I get a positive, and then z minus 1 squared. When n is equal to 3, I get a negative, then z minus 1 to the cube, and we continue. We're looking for the term where we have z minus 1 to the minus 1 power. We can see that when we multiply this 3 times z minus 1, we're going to have a z to the minus 1 to the minus 1 power. None of these other terms will contribute when we multiply by this 3 over z minus 1 or when we multiply by 5, which makes 3 our residue. So I've noted that here, B1 is equal to 3. Our next and our last problem is to evaluate the integral of f of z equals z to the 5th divided by 1 minus z cubed around the circle, absolute value of z is equal to 2, described counterclockwise. I have my f of z written here. Now I want to multiply by 1 over z squared times f of 1 over z. So I have my 1 over z squared times f of 1 over z. Plugging in 1 over z here for the z to the 5th, I get 1 over z to the 5th. And then plugging in 1 over z here, I get 1 over 1 minus 1 over z cubed. I multiply my z squared and my z fifth here to get z to the 7th, and then I multiply my z to the 7th times 1 minus 1 over z to the cubed, and I get 1 over z to the 7th minus z to the 4th. I factor out my z to the 4th, and I get 1 over z cubed minus 1. The singularity I am concerned about is z equals 0 because that's my residue at infinity theorem. So I'm centering at z not equals z. So my 1 over z to the 4th, that's in good form. That's in my z minus 0 form. This here is in the form for my summation formula. Over here, I just need to introduce a negative 1 so I can have 1 minus a simple function of z, which will be z cubed. So I introduce my negative 1, and then I have 1 minus z cubed. So I'm going to put my negative 1 with my 1 over z to the fourth in summation n equals 0 to infinity z cubed to the n, which gives me minus 1 over z to the fourth, and then I have 1 plus z cubed plus z to the sixth, right? When n is equal to 2, when n is equal to 3, I get z to the ninth. And now looking for the coefficient of my z to the minus 1 term, I get z to the minus 1 when I multiply this minus 1 over z to the fourth times z cubed, which means my residue is minus 1, and then my closed curve integral then is equal to my minus 1, that's my residue at z equals 0, times 2 pi I. To review what we have covered in this video, we covered residues at infinity, and this was a theorem here, which was very similar to our Cauchy residue theorem, except that instead of summing up all our residues for each of our singularities inside a closed curve C, we just calculated one single residue. That was the residue at infinity, which is equal to the negative residue at z equals 0 of 1 over z squared f of 1 over z. We worked this example where we evaluated the integral of f of z equals 5z minus 2 over z times z minus 1 around the circle with radius 2 described in the counterclockwise direction. So the first thing we did is to evaluate this integral. We need to calculate the residue at z equals 0 of 1 over z squared f of 1 over z. Here's my 1 over z squared, and then I plug in 1 over z into f of z, and I get 5 over z minus 2 times 1 over z times 1 over z minus 1. Algebraically, I will let you verify these steps here, but I essentially get this into the form where I could use my summation formula. This factor here becomes my 5 over z minus 2, and then I use my summation formula here, which is summation z to the n. I expand out my summation because now I'm looking for the coefficient of the z to the minus 1 term, and I see the coefficient then is equal to 5. It comes from the 5z times the 1. My residue is 5. This again is the residue for z equals 0. So according to my residue formula, my closed curve integral is equal to 5 times 2 pi I, which is 10 pi I. So again, this formula we also did in an earlier video and also in the details of our video using the Cauchy residue theorem. We had to expand around z equals 0 as well as around z equals 1 because we have these two singularities. And remember, we expanded f of z, not the 1 over z squared f of 1 over z. But we had to do two expansions because we had two singularities. So the more singularities you have, the more time you can save by using this residue at infinity, because then you're only calculating one residue. So that's it for this video. Thank you for watching.